Alright, so I have a situation here where we've got two pool balls that are in motion. So our initial part of the motion here is we've got pool ball B moving with a certain velocity to the right, and it's moving at a much faster velocity than pool ball A here, but pool ball A is also moving to the right. Well, at some point, since this ball B here is moving much faster, it's going to catch up to A and it's going to collide with A. And after they collide, we get this situation here where ball B is moving back the other way with a slower velocity, and ball A is moving this way with a faster velocity than it had at the beginning. So, if we look at this in terms of what we've been talking about with momentum, we can say that ball B here, and actually I'm going to change this color, ball B here, we know has a certain momentum. We use the symbol P for this, for momentum. Ball B has a certain amount of momentum, and actually I'm going to use, I don't know why I used white for that, I'm going to use red for this. Ball B has a certain amount of momentum. And remember that momentum is the mass times the velocity. So we would take the mass of ball B, multiply it by how fast it's moving. That's the momentum ball B has. And right now, at the start of this situation, it has more momentum than ball A here. Ball A has less momentum than ball B. And when they collide, we call that situation there that there's an impulse. In other words, both of these objects are going to change their momentum because of this collision. Because we know that from Newton's third law, each of these objects are going to exert a force on each other. So when these two things come into contact, ball B here is going to put a force on A, and A is going to put a force back on ball B, and those forces are equal, but they're in opposite directions. So let's see if I write this out. A is going to put a force on B in this direction, and B is going to put a force on A in this direction. But they're the same magnitude, just different directions, right? So we've got an impulse felt on A, an impulse on A by B. And remember that impulse we learned last week. Impulse is force times the amount of time that it's in contact with it. Force times the amount of time. That's the impulse on A. Well, if this is the impulse that A is feeling from B, that means that the impulse that B is feeling from A is the same amount, since we just got done saying that the force, because of Newton's third law, the force is the same, just in different directions. So if I were to do the impulse that B feels from A, it would be negative F delta T. So the same magnitude, but just different directions. Whatever impulse B is putting on A is going to be the same impulse that A is going to put back on B. And so they're feeling, essentially, both these objects are going to feel the same change in momentum. So we're going to make a note of that over here. So note over here. So the impulse, which remember impulse is change in momentum, the impulse for each ball is the same. But opposite directions. So impulse on each ball is the same, but opposite directions. Now, that brings us to this last part here. After we get this collision, or this impulse, each ball now is going to have a different momentum than what it had at the beginning. So if we think about this, ball A had some positive momentum this way. Well, here's the change in momentum for ball A that it's going to feel. It's going to feel a a positive impulse this way. So we're going to add this to whatever momentum it had at the beginning. And so here, it's got more momentum going this way. So it's now got more momentum than it had at the beginning because this is the change in momentum that it feels. And so now at the end here, it has more momentum than it had at the beginning. But for ball B, here's the change in momentum for ball B. It's negative. And so I'm taking away some of this momentum that it had here at the beginning. And so for ball B, we see that it is now moving at a slower, or it has less, I should say, slower velocity, but it has less momentum than it had at the beginning because this is the change in momentum that ball B feels. Now here's the thing, since each of these balls here feels the same amount of impulse, the amount of momentum in this system, so if we say that the system is just ball A and ball B and that's it, that's our system that we're looking at, we're not looking at anything else, we're looking at just ball A and ball B, that's our system. Well, our system here, we should say that the momentum in this system, so I'm going to say the initial, this is final. My momentum in the initial system would be, so let's say initial momentum of the system is equal to the momentum of B, plus the momentum of A. So that this plus this would be the total momentum of our system of ball A and ball B. And then my final momentum of the system would be, here's how we would write this. We would say the new momentum, so P prime, basically saying the momentum that it changes to for B, plus the new momentum of A. Whoops. Trying to change a lot of colors here. The new momentum of A. So P prime is just saying the new momentum from the beginning. So what we can see here is that whatever momentum I had at the beginning, and after this change or after this impulse, is going to be actually the same amount of momentum that I have here at the end. So what we can do is we can set these two things equal to each other. So what I can have here is, so the momentum of B plus the momentum of A is equal to the momentum of the new momentum of B plus the new momentum of A. And this right here is the law of conservation of momentum. So the law of conservation of momentum basically says that for any closed system, so if we say that this is a closed system, just looking at ball A and ball B, any changes, anything that happens within that system, the momentum is going to be conserved. So even though the momentum for ball B changes, the momentum just for ball B changes, For the entire system, momentum is conserved. So whatever momentum these two balls together had is the same amount of momentum that these two balls together have at the end, even though individually they change. So we can actually use this to solve some different problems. So if we look at an example kind of similar to these up here, let's say we look at some train cars. So we've got some train cars here, and let's say that in this situation we've got train car B here, and let's say that the mass of this is 300,000 kilograms. And we'll say that the velocity of it is 2.2 meters per second. And for this guy over here, the mass will be the same thing, 300,000 kilograms, but the velocity is, this one is just at rest, so it's not moving, so 0 meters per second. So we've got a train car over here coming in pretty quick. We got this train car just sitting here at rest at 0 meters per second. They collide with each other, and after they collide with each other, they are now both moving as one thing, as one object basically, to the right, but just at a slower velocity, okay? And so let's say we want to figure out what then is the final velocity that these two cars have after this collision, after this impulse. And so what we can do is we know, based on this up here, that whatever momentum these two cars had together at the beginning has to be the same as the momentum they have here at the end. So if I just take, I'm just going to use the color white from now on because I'm sick and tired of changing between colors. If we say the momentum of car A plus the momentum of car B is equal to the momentum of each at the end. Well, we know that momentum is equal to mass times velocity, so I'm going to kind of simplify this a little bit. So we've got the mass and velocity of A plus the mass and velocity of B is equal to the mass velocity prime of A plus the mass velocity prime of B. All right, so now from this, though, we can kind of simplify this a little bit further, because if we look at this, my train car A here at the beginning has 0 velocity. It's not moving anywhere. So if I come back down here, that means the momentum for A at the beginning here is nothing, because it's going to be mass times 0, so that's just going to go away. And the other thing is, if we look at the end here for the final part of it, the masses of the train cars are the same, and at the end here, they're acting as one solid thing. They're acting as one solid thing, and they're going to be both moving at the same velocity. So if they're both going to be moving at the same velocity, and they both have the same mass, what I can do is I can simplify this part of this equation as well. And I can change, this is going to go away, so I'm just going to have mvb. I'm going to combine these two since the velocities are the same and so are the masses. It's going to be 2mv prime. So now I've simplified this equation down to this, and so now I can solve for the velocity. Should be velocity prime. Here's what we're trying to look for, because I know the masses and I know the velocity of car B at the beginning. So let me rearrange this again. Divide by 2m, divide by 2m. Mass is going to cancel, so it's just going to be velocity of car B divided by 2 is equal to the final velocity. Plug in the numbers. Let's see, the velocity was 2.2 meters per second for car B, divided by 2 is equal to velocity. So the final velocity of both the cars together is just going to be this cut in half, so 1.1 meters per second. So that, which makes sense because this car was not moving at all and this car had a speed of 2.2. So after they collide, because of that impulse, their final velocity, it makes sense that it would just get cut in half to both of these cars having a velocity of 1.1 meters per second going in this direction.